record on this computer here. I think it says that we are recording. And now I'm going to do some slides here. And we're 3 seconds in. Okay. Well, thank you for the introduction. Good morning. It's a great pleasure to be here speaking at the SMPTE 2020 conference under this very interesting year. My name is Paul Debevec, and I'm a senior scientist at Google Research and an adjunct research professor at the University of Southern California's Institute for Creative Technologies. And what I have to talk about today are a number of techniques that we've been working on that basically try to join real and virtual worlds using illumination. And these express themselves with things we do with our light stages, with light fields, and have applications to virtual production. And a lot of this work originally came out of some things that I was involved in as a postdoctoral researcher at UC Berkeley back in the late 1990s. I directed a couple of computer animations that used a technology that I'd worked on called image-based lighting. And in these animations, which had computer-generated objects, they were illuminated by measurements of light in the real world. And the measurements were done by taking high dynamic range panoramic photographs and then using global illumination ray tracing algorithms to illuminate these CG objects like these spheres on top of a pedestal in the UC Berkeley Eucalyptus Grove, or these monoliths and spheres inside St. Peter's Basilica, which was reconstructed as a photogrammetry model, as realistically as possible to look just like they were really there. And if you look at a behind the scenes photo, you can see the pedestal here in the rendering with natural light scene and how I've texture mapped these emissive high dynamic range images on surfaces surrounding the scene. So when I rendered it using the radiance renderer, it would be illuminated by these kind of glowing images that surrounded it. And I thought that if I ever wanted to make a movie that would have humans in it, people, rather than just computer-generated objects, it would be great to find a way to illuminate real people with measurements of real light. And that was the motivation for one of the early projects we did at the USC Institute for Creative Technologies, which was to build a lighting reproduction system. Our Light Stage 3 device had 156 RGB color LEDs, computer controllable, that could display a low resolution version of omnidirectional high dynamic range images of real scenes or virtual sets on the actors. So they'd be illuminated just right, and then when composited in would look like they were really there. So here you can see a couple of actors composited into the UC Berkeley Eucalyptus Grove, the Galleria degli Uffizi in Florence, Grace Cathedral in San Francisco. And hopefully in all these cases, the lighting on the actor matches the lighting you see in the background, which in this case was composited in using an infrared compositing system with this infrared reflective black cloth and a beam splitter camera system. We published a paper on this technique at the SIGGRAPH 2002 conference, and you can see a couple of examples in the video here. This is the control system program. It was actually a real-time program that could adjust the rotation of the environment and the view that you have in it according to how you spun the actor around on a little platform. This is Emily lit by the light of Grace Cathedral. There was the infrared mat, and here she is composited into the scene. And if we go a little bit further forward, we can see another animation with Alana here being illuminated by animated light so that she walks into shadow and back into sun as she walks along this virtual set of the colonnade of the Parthenon. This technique actually and this very system got used in the process of creating a couple of feature films. One of them was Spider-Man 3, where all of the actors in costume who were getting scanned downstairs in Light Stage 2 for their reflectance fields were brought upstairs to get reference of what they would look like in various illumination environments, real world lighting environments. So the digital characters could be proven to match how the real characters look in the same lighting. And then another film was The Social Network, the David Fincher's film, which had as the antagonists the Winklevoss twins. They were supposed to be identical twins, but the second one in the back here was played by a different actor. So they did a number of face replacements of actor Armie Hammer to make it look like there were two of them. And Armie Hammer was actually brought to our laboratory where we played back animated high dynamic range images onto their faces so that he would be illuminated by the light of these locations where they'd shot the scenes. And then when this face would be composited onto the face of the other actor, the lighting would match. And the final work was done by Lola Visual Effects. And you can see that by doing this controllable illumination driven by the light of the real scene, that you're able to do relatively realistic illumination on faces, and it matches up pretty well. Some of the other contributions in the paper were actually made in the future work section, where some of the current limitations of the system and some of the directions for developing this into a fully realized virtual production system were discussed. And these included having ways of simulating the sun, increasing the lighting resolution, simulating spatially varied light, recording and reprojecting light fields, making a big stage, simulating the shadows the actors would have on the ground, improving the matting, the color rendition, and having cinematographer-friendly lighting tools. And some of our quick follow-up work to this also looked at changing lighting in post-production. So that's what I thought I'd focus on for the next part of this talk, is talk about some of the directions we've taken this since then that we pointed the way for. And you can see this kind of vision that we showed at the end of the SIGGRAPH 2002 talk did discuss building a larger version of the stage and maybe having the camera on a jib arm that's motion controlled and can move it around, or at least encoded, so that you can match virtual and real viewpoints as you're matching the real and virtual lighting. We actually had the opportunity at the USC Institute for Creative Technologies to build something pretty close to this vision we had in 2002 for a Chinese visual effects company called SUV, located in Beijing. And a few years ago, we built an 8-meter version of this light stage with about 1,000 multispectral lights, a light up floor. There was a green screen that they use in there to do the compositing. And taking a look at this in operation here, I got to visit recently and actually be part of a demo. They use this to illuminate actors and then add them into scenes of TV shows that have already been shot, or for special visual effects sequences in feature films. And they have ways of quickly switching the lighting in the stage from one scene to the next. And one particular use case is to add an actor to a scene who was never there originally, but get the lighting right. And so with me in the chair there, they actually were able to film me in a way that I could be integrated into a scene of these other actors. And hopefully the lighting on me, even though I'm in their light stage, looks like it matches the lighting on the other actors. And when it cuts to me, it looks like it's in the same kind of illumination and I was really there. I won't show you that full sequence, but I will show you some work that they did for a long TV series where this actor playing the doctor actually was added into the show after the entire show had been shot for various production reasons. And you can see that there's lots of compositing, and hopefully he looks just as realistically there as any of the actors, even though he wasn't originally on set. The magic of having this controllable illumination sphere, this image-based lighting system, is that they can quickly go to a different lighting setup at literally the press of the button, and they can get 80 to 100 setups done per day. They were able to add this actor into an entire 60-episode TV series in just a couple of months, which is an enormous amount of work to get done at this level of quality. Another limitation that we found when we were building the system is that since we only had 156 lights, that if you looked closely in people's eyes, you could see the reflections of the individual light sources. And that's something that we knew we'd eventually want to address if we wanted to do close-ups, or if we wanted to do, if the person happens to be wearing some part of their costume that's very shiny. And right around that time, LED panels became available, and we investigated using those as image-based illumination for virtual production. In fact, I got asked if I could help figure out a way to play back lighting on Brad Pitt's face for a test the Digital Domain wanted to do for The Curious Case of Benjamin Button. And the sketch that I did of creating a virtual production stage to illuminate Brad Pitt's face with image-based lighting being played back on LED panels looked like this. It basically surrounded him around the front with kind of a semi-cylindrical setup. And then we even did a test with an LED wall that was set up by Digital Productions up in the Valley. Thank you very much. You can see here's our lighting reproduction paper displayed on there. You can see this old CRT monitor kind of gives an indication of when this was done back in 2004. And we went in with our light meters and took a lot of reference photographs and displayed pieces of light probe image onto the LED panels and then had that illuminate an actor's face. We took pictures of them. And then by looking into their eye reflections, we showed that even with the 9mm LED panels that were available at the time, we could get good eye reflections, which we felt really good about. And this technique didn't end up getting used for the curious case of Benjamin Button, but it did indirectly lead to us having an opportunity to work with Alfonso Cuarón and Emmanuel Lubezki on a movie called Gravity, which would also use image-based lighting playback on the actors to photorealistically integrate them into virtual sets. And one of the tests we did was at the light stage at Otoy up in Burbank, where we played back illumination environments on the stand-in actors who would eventually be Sandra Bullock and George Clooney. And Alfonso Cuarón directed this test shoot and got to experience what it's like to have your actors surrounded by LED controllable illumination to get the lighting right on the composites. And eventually Framestore built the light box, a 10-foot by 10-foot by 10-foot cube of LED panels at Shepperton Studios in England, where they shot the film, so that they could play back pre-rendered scenes rendered in global illumination software Arnold to light the actors' faces with the illumination of the sets that they would be composited into. And the visual effects won the Academy Award for Best Visual Effects that year. They were fantastic. And you could really believe that those astronauts were spinning around, tumbling through space with all the things you saw in the background actually being their sources of illumination, that they were really well integrated. So this is still only a modest sized stage that can illuminate maybe the head and torso of an actor. Eventually, our idea was we wanted to be able to illuminate multiple actors in small amounts of set pieces. And the biggest production to date that has surrounded actors with LED panels is a Chinese production called Asura, which came out a few years ago, where Charlie Idriaga, the visual effects supervisor, worked with the Ningxia Film Group Corporation to design and build, back in 2016, an enormous LED panel stage that was 85 feet by 68 feet by 27 feet tall with LED panels everywhere, including the ceiling and the floor. Now, of course, you don't actually want to stand directly on LED panels because they're not quite high enough resolution for that and they don't receive shadows well yet. But what you can do is build a little piece of the set, in this case, some grass here. And in this outdoor scene that's supposed to take place on this beautiful mountaintop, the actors are surrounded by images of the light from the beautiful outdoor scene. And they had a clever process of tracking how the cinematographer would move the camera around and then placing blue screen just behind the actors in the camera frustum so that they could do a high quality composite of a very high resolution version of the environment. And this is good to have in the event that you want to have more control over your final output and potentially get around problems with the LEDs being not quite high enough resolution to appear directly in the background of your shot. Once it's all composited, you can see that the actors are realistically lit for the scene, and with the set extensions and the illumination and the virtual background, it looks like they were actually shot on the mountain. They shot lots of scenes this way, including stunt sequences where the actors were on wire and flying through the entire volume, and a big throne room scene at the end where you can see really elaborate virtual sets around the actors as they have a big showdown there. The cinematographer-friendly tools were actually quite impressive as well that they developed, where an iPad could be used to virtually move any kind of lighting around the actors in real time and adjust it. Basically having very efficient motion of illumination around the actors. And this could also be used for special visual effects techniques, where in this case, there's this kind of glowing creature moving around the actor, and you can see that that is being affected here in the final version of the film. We've since, in Los Angeles and other places, seen a flurry of new excitement for using image-based lighting techniques with LED lighting reproduction for virtual production, including Lux Machina's LED wall demo that they showed at SIGGRAPH 2019, and a number of large-scale productions such as First Man and Westworld and The Mandalorian, which have been using these techniques to great effect for today's filmed entertainment. And it might really take off and be a very standard way of doing some of this work. There are still some limitations that we're struggling with. And another one of them is that these red, green, and blue LEDs that you find either in these individual light stages that we did back in 2002 or in these LED panel stages don't have particularly good color rendition. So they weren't really designed as illumination sources, they were designed more as display surfaces. And as a result, there wasn't a lot of attention paid to having a particular even spectrum of illumination coming out. When you mix red and green and blue to make white, you don't get a particularly even spectrum. You just get this kind of, tight lump of red and tight lump of green and tight lump of blue spectrum. And there's no way to mix red and green and blue like this to get something that well approximates this relatively flat spectrum of daylight or tungsten illumination. And that's kind of sad. The result is that you get relatively poor color rendition on a lot of different surfaces. And in particular, one of them is human skin. Human skin, this is the reflectance spectrum of skin, has some interesting spectral detail where the blood in the skin, the hemoglobin, starts to absorb the shorter wavelengths. And here you can see it's reflecting a lot of red, but then there's this precipitous dip here. And that happens right between where the red and green LEDs aren't producing very much light. RGB LEDs don't produce anything in the yellow area of the spectrum, and that's where the interesting stuff in skin is happening. And so the result is that it kind of missamples and misrepresents what skin's really doing there. And you're missing some of that illumination. As a result, when you illuminate an actor with red, green, and blue LEDs, they tend to look a little bit too color saturated and maybe a little bit toward the magenta or pink side of the spectrum. Where if you light them with full spectrum white LEDs, which use phosphors, they don't have all the color control that you might want, you'll get a very different appearance. And when you need to, in virtual production, both see the colors directly in the background and also the effect they have on people's faces, this can be a real problem. So we started trying to address that back in 2003 when we built a custom 9-channel LED light by taking apart 3 RGB light sources, all from Color Kinetics. And we added all the other colors of LEDs we could find and made some that we couldn't. The yellows we made by using white LEDs and filtered them down with yellow filters. So with this 9-channel light source, we actually showed in a research paper we published back then that even using relatively simple techniques for reproducing various light spectra, you can get a far better result with a 9-channel light source that you see on the right, simulating this lighting condition in the center, than you can with an RGB light source. Here we're trying to mimic the effect of tungsten light on the left and fluorescent light on the right. We've since gotten to push this quite a bit further in some work at USC ICT, where we built an entire light stage out of multispectral lights that don't just have red and green and blue LEDs, but they also have amber and cyan and white. And this is Chloe Legendre, our graduate student, who published a lot of this work as part of her PhD thesis, showing the illumination system that we have surrounding people with multispectral light. And the research paper that we published at SIGGRAPH 2016 showed that if you record your scene lighting, of course with mirror balls and cameras, which record red and green and blue, if you record your HDRI maps, not just with red, green, and blue channels, but also images of color charts aimed in different directions, you can figure out how to reproduce the color rendition properties of the light all in the entire sphere, driving the light stage to replicate the lighting conditions, no matter what kinds of illuminants are out there, and usually do that quite accurately. These two results show the results of using the light stage to replicate two daylight lighting conditions, one that's kind of in the late afternoon getting towards sunset on this actress here. This is the actress lit in the real environment. We then captured the light as she stepped out of the way. We shot a background plate, and then we reproduced that light in our light stage on her face. This is actually her in the light stage composited into that environment with no color correction whatsoever, and it matches quite well. This is another actress. She was lit under a shady condition. You can kind of see some of the blue sky reflecting in her forehead here. We recorded the light. We reproduced that in the light stage. You can see the blue sky reflecting, simulated in her forehead here, and she matches into the environment. And it's close enough that actually for a while I had the images on this slide reversed until it was pointed out that I had the real and the virtual in the wrong places. They look close enough for at least to fool me. This seems like a very useful thing to be able to have, where the lighting that you want, whether you've captured it or whether you've rendered it with physically based rendering, you can guarantee that it is going to produce the expected effect on your actors' faces. In all of this work, though, we're still assuming that we're going to record our actors knowingly from the right position, from the right angle, and in the right lighting. And we can open up a lot of other post-production possibilities if we had technology that allowed us to change the lighting after you've already recorded the actors, or to change the viewpoint after you've recorded the actors. And one thing that we've done with the light stage that we've built at Google is that we found a way to record people from a set of lighting directions that illuminate people in a way that you can observe their surface orientations. We actually record people from an array of cameras surrounding them from 100 different directions, and we bounce between two lighting conditions that give you a record of people's surface orientation that allows us to compute new lighting on the actors. So these here are folks who have been recorded in our light stage as kind of digital avatars, and we're playing back what they did in the light stage, rendered into virtual sets, lit by the light of these virtual sets, and then from the viewpoint of a virtual camera. And this is another technology you could imagine using in virtual production. It's not quite ready for close-ups yet, but it can produce dynamic performances of pretty much arbitrary things and integrate them into scenes pretty convincingly. In fact, some versions of the technology and data from this light stage has been used in conjunction with machine learning techniques to help you re-illuminate your own photos on your own cell phone. The portrait light feature that's launching with Google's latest Pixel phone uses machine learning trained with light stage data to allow you to add a virtual fill light from any direction that you'd like to augment the lighting in your photographs. And maybe that will eventually help us get the lighting right with a bit of help from machine learning as well. The last thing that I'd like to talk about today is directly on this idea of changing the viewpoint in post-production, and particularly for an application in the area of virtual reality. Virtual reality headsets have the ability to change what they show you as you move your head around in the scene. That's great for game engine content, but for real photographed content, normally, even if it's in 3D and omnidirectional, it still is shot from one particular point of view. And as you move your head, the viewpoint doesn't adjust. Back in 2015, I suggested that the right way to shoot this material would be to create a sphere of small cameras to record all the rays of light coming into a volume, and then use light field rendering to generate the new viewpoints that you would need anywhere inside that sphere as you lean around watching your virtual reality experience. And that this would be both more immersive and also more comfortable because everything matches how you're actually moving your head. I'm very happy to report that we've been able to build this technology at Google, which we call our Deep View video system. And those were some of my colleagues that I've gotten to work with. So I'm very talented computer vision and computer graphics engineers. And what you can see here is video of our friend Libor in his studio and our friend Alexa doing some of her artwork, where the viewpoint of this video is being moved around virtually, not just the rotation, but also the position of the video, quite realistically, with quite high quality, and arbitrarily after the fact. We can even pause the video and move around within the scene, which is something normally you can't do. The way that we shot this was by constructing a special video camera that had a number of different views. Go forward here a little bit. Here's somebody in virtual reality enjoying this scene and being able to move around and look around it. Here it is running in a web browser as well. And the camera that we built actually wasn't very expensive. It's about $6,000 of action sports cameras, 3D printed, attached onto a $200 acrylic hemisphere. They're hooked up with synchronization cables, and when we press record, they all start recording, and you get 46 videos of the scene looking in different directions, each about 18 centimeters apart. We train a special neural network machine learning algorithm to transform these 46 videos into about 100 spherical layers of red, green, blue alpha channels, which replicates the appearance between all of those different views that we shot and all of the views that we would have in between them. And for compression and transmission and rendering, we reduce this 100 layers of spherical shells into about 16 layers of depth mapped meshes, low resolution geometry with high resolution RGB alpha textures that can be compressed with temporal stability, transmitted and rendered in real time, even now on mobile virtual reality hardware. All of this data gets placed into a texture atlas, which basically becomes either a 4K or an 8K video stream, depending on how many pixels per degree that we want to have in our final results. And the result is you can now record video and watch it in virtual reality and feel far more like you're really there, able to actually move around in the scene, to lean forward, look around an object, tilt your head and not have the views separate from each other, get correct stereo cues when you look up and when you look down, which doesn't work in traditional omnidirectional stereo. You can see we estimate high quality depth maps, which can be used for compositing or visual effects techniques. And our techniques even are pretty good at representing specular reflections, like the shine on the hood of this car or in this mirror in this living room scene in a realistic way. So if you'd like to try out light field video yourself, we have two things you can do. Here's a website to our Deep View video site. And you can either try it out on our web viewers, which will come up right there, and you can move around the viewpoint with the mouse, or you can download for free a virtual reality headset demo that'll work on a Vive or a Rift or Windows Mixed Reality, and try out some of our test material with light field video for yourself. If you have anything that you think that you'd like to use it on, please get in touch. And to end, I'll give you a couple of websites there at the bottom, and I'd like to thank the SMPTE organizers and the many collaborators that I've been very fortunate to have in doing this work. Thank you so much. Okay, it's a little bit over. I think it was pretty good. I'll let you edit it down if you need to. Thanks.